So the aim of this part of today is to look at what we mean by power functions and exponential functions, and then start thinking about how we can use logarithms to get these functions, these power and exponential functions, into a form y equals mx plus c, which you might recognize as the equation of a straight line. So that's what we're aiming for. We're aiming for a straight line graph, because if we get a straight line graph, we can find the gradient of the line, which gives us m, and where it cuts the y-axis, which gives us c, and from that we can find some information about this power function. We'll look at some examples of some power functions and some exponential functions. You'll see they're nowhere near straight lines, so what we're aiming for is trying to get these to look like straight lines. In fact, this idea of getting a straight line graph applies to any type of function, but we're going to apply it particularly to these power functions. So that's the aim. So first of all, let's have a look at what we mean by these power functions. So power functions have the form y equals x to the a. So some power a. So our two variables, the independent and the dependent variables, still x and y, but x is now raised to some power. So an example of that is x squared, which we've seen, the quadratic function. And we know that looks like a parabola. So that's an example of a power function. But it could be x cubed, it could be x to the 4. And if you applied it to an engineering scenario, particularly if we're thinking about gases, expansion of gases and things like that, we actually find that the powers are not whole numbers, 1.7 or something like that. So these powers, we need to be able to find out what they are. And the way to do it is to plot the graph and trying to get it to look like a straight line graph, so we can find the missing number, and we'll look at that. The other type of graph that we're going to be interested in is the exponential function. And that has the form y equals a to the x. So in other words, this time the two variables y and x, the independent variable x is the power. So we've got some constant a raised to a power x, and that's an exponential function. It's called the exponential function because the exponent, which is what we sometimes call the power, is where the independent variable is. That has a similar shape to the top one, but in that case x is actually in the power rather than the power being the base. So in the power functions, x is the base. To investigate these functions, we use logarithms. If we have something like y equals x to the a, for example, some power function, then the logarithm of y equals the logarithm of x to the a. So I take the logarithm of both sides. And logarithms are to do with powers. And the laws of logarithms enable us to play around with this thing. So the laws of logarithms. In fact, what we'll do is we'll put the laws of indices and logarithms together because they are combined. So these laws, we split the page into two. We've got if we've got x to the a multiplied by x to the b, from the laws of indices, you add the powers. That becomes x to the a plus b. Because logarithms are powers, then we say that the logarithm of a times b is the same as the logarithm of a plus the logarithm of b, because logarithms are powers. Similarly, x to the a divided by x to the b would be minus the powers. So with logarithms, the logarithm of a divided by b is the same as the logarithm of a minus the logarithm of b. X to the a raised to another power, b, if I've got one power raised to another power, x to the a times b. So, and this is the useful one for us, this is really the key one, the log of a to the power b is b times the logarithm of a. We just multiply them together. And this is the important one that we're going to be using. So what we have is a situation where I've got one power raised to another power, then I can turn that into a multiplication. So if I turn my power function into a logarithm, then I can actually turn the power into a multiply. So if we look back at this, y equals x to the a, here, if I take the logarithm of both sides, I've turned both sides into powers effectively. So I've got one power, log of x, raised to another power a, so I can use the law of logarithms and bring this a down and turn it into a multiply. So that means, so therefore, the log of y equal to, we have the log of, what did we have? Log of x to the a becomes the log of y equals a times the log of x.